All right, let's get right into it. Welcome to The Explainer. Today, our core goal is to totally pull back the curtain on how artificial intelligence actually solves problems. You know, we constantly hear about AI doing these incredible, almost magical things, but if you look underneath the hood, it's not magic at all. It's really about mathematics, strictly structured rules, and navigating these wild, abstract landscapes. So today, we're going to break down the exact mechanics of how that whole process works. Here is our roadmap for today. First up, defining artificial intelligence. Then, we'll dive into problem solving and state spaces. Third, we'll tackle the classic water jug problem. Fourth, navigating with search strategies. And finally, number 5, getting smart with heuristics.
So, part 1, defining artificial intelligence. What exactly are we building here?
John McCarthy, the guy widely considered the absolute father of AI, defined it as the science and engineering of making intelligent machines. Now, I really want you to notice that word engineering. AI is an active, structured pursuit. The goal here isn't necessarily to perfectly clone human biology. Instead, it's about making computers do things that, well, right now, people just do better. It's all about computational intelligence. So when you fire up ChatGPT or talk to your smart home assistant, you aren't talking to a biological brain. You're interacting with a highly engineered, purely mathematical solution designed to hit a very specific goal. Moving right along to part 2, problem solving in state spaces, or how AI translates the real world. To a computer, solving a problem basically means exploring what we call a state space. Think of a state space as a giant universe containing every single possible configuration for a given problem. Take a super simple game like tic-tac-toe. To us humans, it's just a fun little game. To an AI, that 3x3 board represents the current state. The operators, those are the legal moves, putting an X or an O in an empty square. The AI completely ignores the fun part. It just sees a mathematical space where it has to move from the initial state, an empty board, to the goal state, getting 3 matching symbols in a row. Now think about how different programs might actually tackle that tic-tac-toe space. A really early, basic approach might just try to memorize every single possible board combination. But for tic-tac-toe, that means memorizing a massive list of almost 20,000 elements. And back in the early days of computing, memory was a huge bottleneck. You literally just couldn't store everything. That physical limitation forced engineers to come up with smarter, look-ahead strategies. So instead of relying on pure brute force storage, a look-ahead algorithm actually evaluates board positions to estimate which move is most likely going to lead to a win. It anticipates the opponent's next moves and picks the absolute most promising path. It's searching intelligently rather than just blindly remembering. All right, part 3, the water jug problem. Let's see how AI solves some classic logic puzzles.
Picture this. You're standing at a tap and you only have 2 things, a 4-gallon jug and a 3-gallon jug. Your mission is to get exactly 2 gallons of water into that 4-gallon jug. Just take a second and think about how you'd physically pour that water back and forth to make it happen. Takes a bit of human intuition, right? But here's the thing. An AI doesn't have intuition.
Instead of intuition, the AI uses something called a production system. It's basically a mathematical engine built on super strict if-then rules. The AI starts at state 0, 0, both jugs completely empty. Then it checks its rulebook. Rule 1. If the 4-gallon jug has less than 4 gallons, then fill it from the tap. Rule 5. If the total water in both jugs is less than 4, then empty the 3-gallon jug into the 4-gallon jug. By systematically applying these operators, changing the state of the jugs step by step, the AI literally forces its way mathematically from an empty start right to that target goal of 2 gallons. Which brings us to part 4, navigating with search strategies. Basically, how does the AI navigate the maze? Having a list of rules is great and all, but in complex problems, if you apply every single rule, you instantly create thousands of overlapping possibilities. To manage that chaos, AI structures its problem space using graphs and trees. A graph connects all the possible states together, but a tree organizes them hierarchically, branching out from one single starting point. In a search tree for our tic-tac-toe game, every layer you go down is called a ply. It represents a sequence of states formed by possible moves, so the AI is effectively visualizing all the invisible branching paths from this exact moment all the way down to a future win. Let's look at another famous brain teaser to see how this builds when we add some really strict constraints, the missionaries and cannibals problem. 3 missionaries and 3 cannibals have to cross a river in a tiny 2-person boat. The golden rule? If the cannibals ever outnumber the missionaries on either side of the river, well, the missionaries become dinner. To solve this, the AI systematically tests boat trips by mapping out safe nodes, and it totally ignores any path that leads to what it calls an undesirable terminal state, which is a polite way of saying someone gets eaten. And by the way, this isn't just a fun abstract puzzle. This exact logic of rigorously searching spaces to avoid undesirable terminal states is exactly how modern self-driving cars figure out how to avoid collisions on the highway.
But how does the AI actually travel through these massive trees? It uses specific control strategies. The main ones are breadth-first search and depth-first search. Think of them as two wildly different tour guides, each with a strict trade-off between computer memory and processing time. Breadth-first search is super thorough. It examines the entire top layer of a tree before it ever goes deeper. It absolutely guarantees finding the best, shortest path, but man, it eats up a massive amount of memory. Depth-first search, on the other hand, just picks a path and drives down it as far as possible before turning around. It's incredibly fast and uses hardly any memory, but the danger? It might blast right past a much better, shallower solution.
Finally, part 5, getting smart with heuristics. What happens when problems hit real-world scale? Those basic search strategies, awesome for small puzzles. But then you get a game like chess. The rules are crystal clear, but the sheer volume of potential moves is just astronomical. The number of possible states in chess actually exceeds the number of particles in the observable universe. Crazy, right? If a computer tried to use brute force, checking every single possible path with those basic search strategies, it would take thousands of lifetimes just to make one move. So we clearly need a completely different strategy. Enter heuristics. A heuristic is essentially the ultimate smart tour guide. It's a function that looks at a problem state and assigns it a score based on how desirable it is. So instead of blindly checking every single possible chess move, the heuristic function makes a highly educated guess. It evaluates the board and basically says, hey, this direction looks really promising. Let's focus all our searching over here first. The real magic of heuristics is all about those trade-offs. These algorithms aren't perfectly omnisciently intelligent. They get their incredible performance by exploiting domain knowledge. They take feedback from the data, choose the most promising moves first, and instantly throw out the terrible paths. Now, yes, using a heuristic means you sacrifice the absolute ironclad mathematical guarantee of finding the single most perfect solution. But the payoff? It finds a highly effective, winning solution in polynomial time instead of exponential time. For computer scientists, that is a massive, massive victory. It takes a problem that would literally take until the heat death of the universe to solve and crushes it in seconds. It beats brute force simply by knowing exactly what to ignore. So we've journeyed all the way from basic state spaces and rigid IF-then rules to complex heuristic guesswork, which leaves us with a pretty fascinating final thought. If the most advanced problem-solving AI out there fundamentally relies on these smart tour guides and highly calculated, educated guesses to navigate impossibly huge realities, are we just building calculators on steroids, or are we engineering machines that are genuinely learning to intuit? It is definitely something to think about. Thanks for hanging out with me on this explainer, and keep exploring.